Okay, so hey everybody, this is a presentation that's been presented at ICNC 2025, and today we're going to be talking about a new concept called integrated communication and computing. So this is a small overview of the content that we're going to cover today. First, we have an introduction, and then we will go through the system model. Then we will go through the proposed receiver structure, some results, and we can also see some further work that we've been working on. So the focus on this presentation is, as I said before, going to be on integrated communication and computing, and we will abbreviate this as ICC to make it easier. So what we do is we design an initial framework for these receivers, leveraging the Gaussian belief propagation algorithm. This is going to be the system model that we work with. So as you can see, it's going to be an uplink SIMO system where we have multiple users or edge devices, doesn't really matter. Each of them independently transmitting both a computing signal and a data signal. And all of that is going to be collected and received at a base station or an access point with N antennas. And you also have K distinct users. So maybe one thing to note here is that we assume throughout the presentation that our computing signal is relatively small. So it's going to be, if our data signal, if we put 100% of our power to a data signal, the computing signal is going to have like 1% of that total power. So this is going to be the system model. All the users are transmitting in uplink to the base station. And we are going to do a receiver structure design at the base station to estimate both the data symbols, so all of the data symbols that each of the UEs are transmitting, and also a computing function So the receive signal is given by equation 1. As you can see, it's very similar. It's very familiar to the communication society, where we have a receive signal Y, a transmit signal X. The channels, we can assume that these are for now Gaussian channels, denoted by H, and some AWG and noise. So we can now define the transmit signal for the ICC paradigm as in equation 2, where we have data symbols. So these DKs can come from any conventional alphabet, for example, QPSK, QUAM, or so on. And you have also this computing signal. So what's also important to see here is that this computing signal doesn't necessarily need to be of any structure. It can be Gaussian variables, for example, but we also see that it can also be preprocessed by some function psi, as you can see here. And each of the UEs can independently preprocess their computing signals before they transmit. So the received signal can now be expressed as in equation 3, where we have this nice matrix form. And as you can see, this D is the data once again, and the S is the computing signal vector. And to make the ARCOMP operation a bit easier, we also assume that these pre and post processing functions are just mapped to themselves, and we just obtain a sum equation 4. So our f of s is going to be the sum of all the SKs that have been transmitted. And the goal of the receiver is going to be to estimate these Ds and this Fs. So we can first express this equation that we had before, element-wise, which is just to say that the yn can be expressed as seen in equation 5. And then the corresponding mean squared errors are given as in equation 6. So as you can see, we have a typical MSA definition for the data. If it comes from a discrete alphabet, it can also be written in this form as seen. And it's the same goes for the computer signal. So since we are going to be doing belief propagation, we can first start with a soft interference cancellation step, where what's new is this bivariate formulation, where when you calculate the soft interference cancelled symbols of the data, you're also going to be removing the effects of the computing signal and vice versa. As you can see, it's shown in red here. So we can now leverage scalar Gaussian approximation to approximate that soft interference cancellation as some noise, and we can calculate the conditional variances as given in equation 9. As you can see here, also we take into account how each signal takes into account the variance of the other signal, right? So for example, in equation 9a, you can see how the computed signal variance is also used in the computation of the conditional variance of the data, and vice versa. So then we can also use the same scalar Gaussian approximation to calculate the belief generation stages, means and variances. So these are the extrinsic means and variances, and these are given as follows. What's also a nice thing to notice here is that unlike in the previous SIC stage, we don't use the other components information here, the prime information of the other variable here. For example, as you see, when you compute the extrinsic means of the data, you only use the soft interference cancelled means and variances of the data and not of the computing signal. And the same goes for variables as well. So we can now take advantage of the fact that we are working with the discrete constellation for the for the uh, for the data signals, and we have equation 12, which is the typical QPSK denoiser for these variables. And for the data, we can also assume for now, without loss of generality, that they come from some Gaussian distribution, and use a typical Gaussian denoiser with the corresponding variance as calculated in equation 13. So we can also incorporate a damping procedure here, which is summarized as seen in the slide. And we do this as typically done in belief propagation algorithms to stop iterations from converging to some local minima. And after we do that, we can now iterate through and obtain a consensus as seen in equation 16a and 16b to get the final results for dk and sk. And we can go one step further and enhance this receiver by designing a combiner for the computing stage. So consider equation 17 now, where we're saying that our f hat of s, so this is an estimate of our fs that we want to compute, is going to be given by some combiner, combined with some data symbols that we've already estimated. So this d hat is some estimated data that we have after the Gaussian belief propagation procedure. So we can now use this data that we had estimated previously to design a U Hermitian, which will enable us to get a nice estimate for our computing signal. So we can do this by formulating an optimization problem, which is given in equation 18. So as you can see, we just want to design a U such that the mean squared error between the f of s and the f hat of s, the estimate, is minimized, right? And the expression for equation 18 is given in equation 19, where, as you can see, we write the sum of s as a vector operation here, and this is the typical formula that's given in equation 17. So formulating the Lagrangian and calculating the partial derivative with respect to u gives you this closed form as seen in equation 20, where your combiner is now just a function of your channel, a function of your computing signal power, and this omega, which is going to be the error covariance of your estimated data. So here, one thing to note is that if your error covariance is small, so as to say, when a Gaussian belief propagation algorithm converges, your error covariance matrix is going to approach 0. So you can, in the limit, approximate this. You can just replace this with 0, and you will get a nice estimate. So of course, since this is an LMSE formulation, you also have the noise power. So that's already been taken into account in equation 20. So these are now some results for what we are proposing. So as you can see on the left is the beta rate for all the scenarios. So we have the underloaded scenario where we have n equals 10 and k equals 2. As you can see, there's no error flow here since we have a lot more observations than variables to estimate. And as you can see, the performance is pretty good. It reaches this linear bound, which is to say, oh, so maybe one more thing about the linear bound is that this black line, which is termed the linear bound, is going to be the bound which occurs when one of the estimates is perfectly known. So for example, in the case of this bit array rate here, we are just saying that we obtain this bound when we set that we know the computer signals perfectly. So for k equals 5 and k equals 10, as you can see, as the number of variables grows, there's going to be some error flow to be seen, because as if you can remember from the algorithm, although we have only 10 observation nodes, we actually are estimating 20 variables here when k is equal to 10. So this is actually an overloaded system. So the same goes for the mean squared error. As you can see, you have varying performances here for the mean squared error. When you have an underloaded system, the performance is best since you only have a sum of a small number of variables. And as you can see, the mean squared error increases since the number of variables you have grows. So this is a result to show that since our algorithm uses such a low complexity Gaussian belief propagation scheme, we can now extend our work to very large systems. For example, these are some results for when n is equal to 200, and the corresponding k's are given by 200, 150 to show all the scenarios. So as you can see, the results remain pretty much the same with the algorithm working across these large systems too. So we can now go a step beyond and see what we can do to directly estimate the f hat of s without estimating all of the sk's, right? So one way to do this would be to consider that our hs plus w is some effective noise. And we can do this because of a fundamental assumption that the s that we have is a low power signal. So it's relative to the data symbols is going to have a lower power. So we can calculate the covariance as given in equation 22. And as seen here, we reiterate the assumptions that S is now a low power signal. And this version can also function without knowledge of the computing signal power, which we didn't have before. So these are now some results that we show. And as you can see, the performance is almost the same. The only difference is that because we are computing the single S now, as you can see in the MSc results for the computing signal performance, you're going to have a much nicer performance even when you have an overloaded system. So as you can see, there's a gap here and a gap over here when k is equal to 10 2. Yeah, so this is going to be it. Thank you for your attention. Do you guys have any questions?
Thank you, Ryan. Guys, any questions?
Yes, I have a question.
Go ahead.
So in all of your results, you said that the power of your computing signal is 1% of the total signal power. Have you tried
Yes.
varying that? Or is there like a trade-off, or depending on how you put it, or is there even an optimal value? Have you looked into that?
Yes, so there is a trade-off, and we have looked into it a bit. But the general idea is that we want to achieve this computing functionality without really disturbing the communication performance, right? So the moment that we start increasing the computing signal power, you're going to get distortions in the communication performance, which is not something that we want to introduce into typical communication systems, so to say, right? And you can actually use that power for communication and sensing too, if you want to do sensing in typical ISAC scenarios too, instead of using it for this computing. So yes, there is a trade-off, and we have looked into it a bit, but the general idea is that we don't want to go too deep with the computer signal power. We want to typically keep it to some one-digit value of the one-digit percentage of the full power to minimize the distortion across the typical communications and sensing waveforms, right? So that's the idea here.
So have you
Well,
tried
can I-
then? Yeah, go ahead.
No, go ahead.
Okay. Have you tried lowering then the percentage, so lower than 1? Is there a limit when the computing part doesn't work anymore?
No, I mean, well, practically, of course, because the more you lower your power, you're not going to get anything, right, at the receiver at the end of the day. So the algorithm will work across a range of powers. I think I've tested it from 1%, from, I don't know, even 0.5% power to around 5% of the full power. It'll still work. Yeah, so that's probably going to be the practical uses for it if it's used in typical communication systems, right?
Okay, thank
Yeah,
you.
yeah, you're
Okay,
welcome.
if I may go back to your answer, Ryan, I would I would disagree with your answer actually because I think
Mm-hmm.
that what your answer is satisfying under the assumption that all the users are
Mm-hmm.
jointly trying to communicate primarily and
Yes,
do computing secondarily. But in a more
yes,
general scenario, if you have like a multi-user scenario where there are some users who only want to do computing and some other users who only want to do communications, and some users that want to do both, then that argument that the sensing signals must be a small percentage of the total power doesn't apply anymore, right? So again, if some of the users are only computing, they're only
mm-hmm.
doing edge computing, they put their full power into that process. So what
Well,
would you?
okay. So just to interrupt you there, it's not that trivial, because if you think about a system where each of the users are going to be transmitting either computing or communication signals or both, if you assume that a typical user is going to just do computing and transmits with their full power the computing signal, then we are going to have problem at the base station, because that strong signal is going to distort all the other signals that are going to come, right? All the other computed signals that are going to come, which are a small percentage. So there's going to have to be some power compensation done at the receiver to somehow compensate for this much larger power coming from one user, and then these other smaller powers which are going to be coming from the other users, right? Do you get my point?
No, I get your point. I mean, so I think that there is a discussion to be held. I mean, there is some further work to be done on precisely
Yes.
what is this ratio. But I'm just saying that as a general rule, I don't think that it's right to say that in all applications the transmitting power of computing signals are a fraction of those of communication signals. That's a particular scenario. That's fine.
Yeah.
But there are
Yeah.
other scenarios too. And this issue that Nicholas mentioned is actually interesting to study what is the then if there are any single kind of power control any thing in terms of trade-offs, and I think that this is still an open issue, an interesting question to look
Mhm.
in a
Yeah.
follow-up.
Yeah. I agree. I agree. Okay. Sounds good.
Any other questions?
I have one question.
Go ahead.
Yeah.
So it's somewhat maybe related, but on the same scope of giving the power to the computing signal. So here you said you give 1% of the total power to the computing signal, right?
Mm-hmm.
And given so what is the actual total transmit power here? So what is the actual value of the actual computing signal that is being transmitted, and what is the distributions of the signal itself? So the
So
computing data, yeah, yeah.
So what we are doing here is that we assume that, as in a typical system, we assume that our transmit power is limited to one. So that
Mhm.
means the full power is unitary, right? So then
Okay.
we can say the power of the data is going to be 0.99, and the power of the computing signal is going to be 0.01. Is that?
Okay, so the actual values then, so the signals are real valued, right? Of the computing
Yes.
signal.
For the
So the actual,
computing, we assume that they're real valued computing
yes, yes. So,
signals.
so the values would be power 0.01, and they are normal distributed in mean zero, right?
Yeah, exactly.
Okay, so they would have actually very, very small absolute values. So like something less than 0.01 or around that, right?
Yeah.
Okay, I see. So then when you have the MSE performance, so the error is, so this is not normalized, this is the absolute MSE, right?
Yes, this is absolute MSC. So even as you can see, when it's like 10 to the minus 3, that means even though the power is small, relatively speaking, it's still like the performance is still all right here.
Yeah, I'm just saying that because if it's not normalized MSE and actually the full actual just MSE,
Yeah.
having the error of 10 to the minus 3 or 2 is
Mm-hmm.
actually compared to the actual absolute value of the computing signals themselves is quite large, right?
Yeah, yeah, right. So maybe a better metric would be to evaluate the normalized mean squared error with respect to the power of the computing signals themselves here.
Yeah. Yeah, I think that might be more informative because what I also noticed was, in a sense, the values of the computing signal is so small, the MSC is actually very sensitive. I mean, the errors is very sensitive. This actually could mean that you're getting quite a large error, right?
Yeah, yeah, true.
Okay, okay.
Okay.
Yeah. I think you should just keep that in mind.
Yeah, in that case, yes, yes.
Yeah.
Thanks.
Okay, thank you.
Yeah, you're
Okay.
welcome.
Okay, guys, thank you very much for the question. Thank you, Ryan, for the talk. I think that's sufficient.
Mm-hmm.
Let's close this.